now. Let's see. Okay. Let me go ahead and introduce our speaker. Dr. Miray Tekkumru Kisa is an assistant professor of science education in the School of Teacher Education at Florida State University. She holds a joint appointment in the Learning Systems Institute, Florida Center for Research in STEM. She is also a core faculty member for FSU Teach, which I'm assuming is a spin-off of You Teach, perhaps, but it's a science and mathematics teacher preparation program. And she is continuing with the theme that has been going on this year, and is building on the work of the presentations by Paul Cobb and Peg Smith. So we are very excited to have her here. She came on the recommendation of Danielle Donnie, and I shared that recommendation with the executive board, and we were all so glad that she was able to agree to present today. So Miray, please, I'm going to stop sharing my screen, and if you could start sharing, we look forward to hearing your presentation.
Yeah, thank you so much, Greg, for the introduction, and thanks so much for having me here today. And thanks, Danny. I didn't know that this came from you, so I really appreciate that. And I look forward to our discussion at the end. And I'm really excited about sharing some of my thinking with you all today. So let me share my screen first. You will first see these mountains. It's just an introduction. Okay, you should be able to, can you see my slide now?
Yes.
Perfect. Okay, so the title of my presentation is Improving Instructional Quality for Rigorous Opportunities to Learn Science in the Era of Ambitious Reforms. So in my talk, I will start with providing some rationale for why to focus on science tasks, and then share some tools for promoting rigorous science instruction, particularly focusing on the task analysis guide in science. And then I will end my presentation discussing some of the affordances and challenges of promoting rigorous science instruction. So as some of you might be familiar, in 2012, National Research Council released the framework for K-12 science education. And this framework describes some aspirations for students learning in science that are based on some key insights from research, which suggests that learning science involves the integration of knowledge of scientific explanations and the practices needed to engage in scientific inquiry. And developing understanding through engaging in the practices of science is more productive for students' learning. Consistently, the framework, together with the next generation science standards, emphasize the integration of these three dimensions in student science learning: disciplinary core ideas, cross-cutting concepts, and scientific practices. Based on this new vision, these dimensions work together to help students build a cohesive understanding of science as students try to figure out phenomena as scientists would do. Then the primary question is, how do we achieve these ambitious goals for students learning science? I argue that we need to rethink students' opportunities to learn in science classrooms. And opportunity to learn has been conceptualized and studied in different ways in the literature, such as exposure to subject matter knowledge, time on task, or content coverage aligned with the standards. I consider it as defined by Greeno and Gristalfi, that is the affordances of a setting for changing participation and practice. They argued that one of the most critical aspects of understanding opportunity to learn comes from the activity system in which students are participating. And classroom activities are generally organized as tasks. So opportunity to learn depends on the tasks that students have to work on. So this focus on tasks was emphasized by Doyle beginning in early 80s. So it's not like a new construct that we are introducing. He argued that what and how students learn are largely defined by the tasks that they are assigned. Just to clarify here, a science task can be part of a lesson, or it may span multiple lessons. It can be a project, an exploration within a project-based unit. It could be a lab or a model-based inquiry that requires students to solve a problem. So any work that students are given to focus their attention on particular science content and practices. So in a recent essay with Miray Stein and Walter Doyle, who introduced this focus on tasks nearly 40 years ago, we revisited the research and theory on tasks and provided some reasons for this focus on tasks in the era of ambitious reforms in science and math education. These reasons include, first, that the tasks are recognizable and consequential units of analysis in the development and implementation of curriculum, instruction, and assessments, all of which are key channels to communicate the vision of instructional reforms. Second, tasks are important because they also constitute a common classroom-based element between the work of the teacher and the work of the students. Third, the focus on tasks helps us understand how to support attention to students' thinking in the classroom because they provide a context for students' thinking and sense-making. And finally, the work on tasks sits at the boundary of research and practice and present a tool that can help to build a common language between the work of practitioners and the researchers around problems of practice. And we know that not all tasks are created equal, and different tasks will require different levels of intellectual engagement from students. Classrooms in which cognitively demanding tasks are used and effectively enacted throughout the lesson are much more conducive to students' learning. So you may now be wondering, especially knowing that you are really familiar with the work in math education on tasks, like how do we identify cognitively demanding science tasks? So my colleagues and I developed a framework, the Task Analysis Guide in Science, or shortly TAGS, for differentiating classroom-based science tasks based on the opportunities that they afford for students' intellectual engagement. So TAGS defines the demand of a science task on students' thinking. And over the last few years, I have also had the opportunity to investigate the cognitive complexity of tasks aligned with the three-dimensional vision for science learning emphasized in the framework. And in collaboration with a colleague, we developed a new framework based on the tags to evaluate specifically the cognitive complexity of summative assessment tasks. In today's talk, I will focus primarily on the tags framework. So the development of the tags was guided by the National Research Framework or guided by the work around the recent vision released by the Framework for K-12 Science Education and the research behind it. And also Miray Stein and her colleagues' work in math education around the cognitive demand of math tasks. So the tags allows consideration of two dimensions that are important for science learning. These are cognitive demand and the integration versus isolation of science content and practices. So you can see the mapping here to the three dimensions. When I talk about science content, I really refer to core ideas and cross-cutting concepts together. And including the second dimension in the text, different from the math framework, was critical because, as emphasized in the recent reforms, these two dimensions, meaning the science practices and content, are at best taught separately, or the practices are not taught at all in many classrooms. This is neither useful nor practical, especially given that in real world, science and engineering is always a combination of content and practices. So now I will walk you through the categories of the tags. I probably won't be able to cover all the details of the framework, but hopefully we'll give you a sense of how it can be used to categorize tasks. So the first dimension in the framework is cognitive demand, which is presented in the horizontal layers of the framework. So according to tags, there are 5 levels of cognitive demand. So memorization tasks are placed at the lowest level. They require exact reproduction of the previously seen materials or committed definitions to memory. Scripted tasks are placed at level 2, and they tell students what to do, and students can complete the task without really needing to think much about the science ideas, and also what they do and why. Here, when I say script, it refers to a well-defined set of actions, sometimes procedures, that a student needs to take, usually in a given order, to complete a given task. So a student basically can follow these actions and reach the desired answer, whether correct or not, without really knowing how and why that script or procedure really led to that answer. Tasks involving guidance for understanding are also cognitively demanding, and they are placed in levels 3 and 4. These tasks have some ambiguity for students about what to do and how to do it. Although a pathway to solve the task is suggested, sometimes explicitly or sometimes implicitly within the task, they cannot be followed mindlessly by the students. So these tasks guide students about what they should do, but students need to really understand or think about what they are doing and why. Doing science tasks are at the highest level, and they require considerable cognitive effort because there is not a well-rehearsed pathway approaching these tasks. They often have multiple entry points for students, and they present uncertainty for students due to unpredictable nature of the process. So the second dimension in the framework helps to identify whether the task involves the integration or the isolation of content and practices. Again, here when I say content, it is about the core ideas in the science disciplines and the cross-cutting concepts consistent and also linking different domains of science. So some tasks foreground scientific practices in their focus. Some foreground science content, and some focuses on the integration of the two. So therefore, categorizing science tasks using the tags requires considering both the integration versus isolation of a task and also the cognitive demand dimension. So for example, a task that involves the integration of content and practices at a cognitive demand level 2 can be categorized as scripted integration in the framework. Tasks at level 3, 4, and 5 are considered as high-level tasks, and other ones at level 1 and 2 are considered as low levels. And here is the 9 filled-in cells in the framework that represent different levels and kinds of student thinking demanded by science tasks. And then again, here are the low and high level categories within the framework and within the actual framework. Here I want to highlight that like cognitively demanding tasks that are integrated that you see in this top right corner require students to use disciplinary core ideas and also cross-cutting concepts as students meaningfully engage in the scientific practices, such as constructing explanations or developing using models. While they use these 3 dimensions together, they try to explain a phenomena as emphasized in the next generation science standards. So in other words, they can position students to use these 3 dimensions together, and they are mostly framed as figuring out phenomenon. So just to make things a little bit more concrete, we will now engage in some collective sense making around the categories of the tags, and we'll have some discussion together so that you can ask your questions. But first, I want to walk you through with a concrete example before you get a chance to look at another example where we will kind of like have a discussion together. So this is an example that you might be familiar either through your own experiences in the classrooms or just like observing or seeing or teaching science. So let's start with a simple one. This task consists of a crossword puzzle that uses terminology related to genetics. Successful completion of this puzzle depends on students having memorized definitions of the terms so that they can link them with the descriptions at the bottom. So for example, here, number 12 says, I know it is small, so it says 2 identical alleles. So students who could have memorized the definitions of key terminology or could easily go and find or Google them could say this is the definition of homozygous. So if you think about this task, it doesn't really require students to engage in scientific practices. So we see a solo focus on science content. In this case, it's about genetics. But it doesn't require students to deeply think about or try to make sense of genetics either. Rather, it requires to reproduce some definitions of relevant science terminology. So this is an example of a low-level task that can be categorized as memorized content. So no focus on practices, solely focusing on science content at a cognitive demand level 1. So that's why it's memorized content. So I know I talked a lot. So let's try to engage in some collective sense making now. I will stop here. I will share a link with you. It will give you an access to Google folders with a science task and also a copy of the text. And then you will soon be sent to breakout rooms where you can think through the categories of the text and also that task specifically. So work with your group members to categorize this PCR task, and maybe, and then we will have a whole group discussion together, both based on your classification of this task and also any questions that may arise around the text. And then after our discussion, I will continue the presentation with some additional thoughts about what it means to implement these cognitively demanding tasks in the classroom. Okay, so let me stop this and share the link with you so that you can have access to the framework and also the task. In the meantime, do we have any questions about what we are about to do or any clarifications about your work in small groups? Are we all good? Here is the link to the Google Drive. Can you access it fine? Any problems? No? Okay, good. Any questions about what we are going to do in small groups?
May I open up the breakout rooms now?
Are we all good to go? Okay. So try to finish it in maybe 5 minutes. If you need additional time, we can try to extend it.
5 minutes?
Yes.
Okay.
Perfect.
Okay, so please join your breakout groups now. Is anyone having trouble? Okay, so Miray, various groups got further along as you'll hear as they report out.
Wonderful. So feel free to use the chat or just feel free to share out like what are some of the discussions? Where did you place this PCR task within the text framework? And maybe your justifications or any questions that might have emerged in your discussion. So feel free to share.
I can jump in there.
Thank you.
We started talking in our group about, obviously there are practices here that are being used for sure. And my initial reaction was that this had some content and some practices, but then we had a non-science-y person in the group and said, well, I didn't get any content out of this. So then we were just going to explore, does this have content or not? And then the breakout rooms ended. So that was a discussion we were beginning to have.
Okay.
To build
What
on
about
that,
others?
actually, I would say to build on what was just said, there were some practices, but we felt that it was more like following a script. That was more, so lots of things seemed to be missing in terms of if you wanted to pull in more information, but it was pretty scripted from our perspective.
Okay. What were some of the script?
We had that discussion too,
It was scripted. So what were some of the things that you noticed or identified as a script in the task?
I would start with the questions that were being asked. Seemed pretty specific.
Okay.
There was a set order to do things.
Good point.
What about other groups? Thank you so much for sharing. I don't know how many groups there were. Like, how many groups did we have?
Yeah.
3?
Well,
okay, did we?
Well, I thought that the previous group was saying how the questions ask you to do specific things. I thought of that as more guidance to, like help more guided in providing more guidance rather than a script, because it's not asking students to look for specific observations or to notice something particular. But where the scripting question came up in our well, we really didn't get a chance a whole lot to talk about this, was, in thinking about, like, could I apply a, like 3 offspring would have, if, like the traditional Punnett square, where I would have 3 offsprings that show the dominant traits and 1 that does not, and while the first cross doesn't quite clearly map out, it looks like it's going in that way. But so that was one of the things that if we were to wonder about that would be it. But if I didn't know that script, I wouldn't know I'd be trying to figure this out.
Yeah. Thanks so much for bringing this idea of like the difference between script and guidance that always comes up when others try the text. So with the script or guidance, we always just like ask questions to students within the task. Sometimes those questions have clear answers, and then like students are really pointed to a particular place, and then when they go to that place, they see the answer. Sometimes they are like asked a set of questions to think through multiple steps to really guide their thinking. So maybe something that we may want to think about in this particular example is which one was happening. So, but before we get into that, I'm just like wondering whether there are any other thoughts or that you guys want to share. Okay, I think I did my wait time. So let me first walk you through this task so that we can kind of like try to make sense of it together. Because I know 5 minutes, it may not be enough to really process all the components of the task. So here students are told that through a technique called polymerase chain reaction, or PCR, scientists can see what's happening at the DNA level. Basically with the pictures or with the diagram, they kind of like really help to help students to see that we are looking at DNA. And then it starts with some puzzlement. Students were puzzled about some breeding results. They were expecting to see a particular kind of gecko, but they didn't see it. So then they are given these PCR results from 2 different gecko crosses. Let's look at these crosses a bit more closely. So students who are provided with these crosses, they may think, okay, there is a male and female gecko, and then there are offsprings, 5 offsprings in this case. And without being introduced to the rules of inheritance or any information about genotypes, so they didn't know anything about genetics, they will try to process this data, right? So one thing that they may think about is like, oh, maybe in the first cross, these 1, 2, 3, 4 looks like female, like the mom, and the others look like dad, because if you look at the lines, they look like they have similar lines. So that might be just like the first thing that the students may potentially think about. And then when they then try to apply this to second cross, they actually see that this doesn't work, right? So then the female and male, they have like the mom and dad have thick crosses, thick lines, but then all the offsprings have thin, so that doesn't really apply. So then they try to make further observations and interpretations about how the genetic information really transfers from mom and dad to the offspring. And hopefully through some discussion, they can start making some deductions of what these tick bars represent. Oh, maybe these tick bars represent 2 thin bars. Each organism has 2 bars, so by attaching some terminology with the help of the teacher, they may say like, they may derive one of the rules of inheritance, which is every organism has 2 versions of each gene. So that might be the first thing that they can start thinking about as they're trying to analyze this data. Next, through their observations, they can also conclude that, oh, maybe one version of a gene comes from a male parent and the other comes from the female parent. So that might be another thing that they may start thinking about. So what we see that the task could potentially afford, again, we are looking at the potential here, is that students actually try to derive the rules of inheritance as they try to reason on these patterns from the PCR data to really try to make sense of like how genetic information is actually transferred from parents to offspring. And then to be able to engage in that sense making, they are doing some data interpretation and finally reaching out the rules of inheritance, Mendelian inheritance. So they are actually becoming familiar with the key terms like the allele, genes, and also getting to know the rules of inheritance and how they apply to explain the inheritance from parents to offspring. So we actually place this task as guided integration because the content that they are focusing on, even though it feels like there is not like we are not naming a particular thing to start with, we are really helping to students through guidance to drive the rules of Mendelian inheritance as they are trying to grapple with this idea of like these gecko breeding results that they didn't know how to interpret. And engaging in data interpretation is really helping them to think about the science ideas and how to apply them to really engage in the sense making. So I will stop here because this is pretty different than some of the discussions, and I just want to hear some of the reactions and thoughts, or maybe questions or confusions.
What grade level?
So this was this task was created for high school biology and mostly implemented at the ninth or 10th grade, depending on when biology is taught at different schools. What about other questions?
I'm going to, Lydia? A question for Lydia?
Yes.
In chat.
Okay.
I actually just answered you in the chat, I think. So this content is grade 8 for Ohio.
Mm-hmm.
Is that what you were going to ask, Constance?
That was one of the things I was going to ask, but I was also going to ask if you were familiar with the Rebop experiments that were done around late 90s with high school teachers regarding genetics.
No, I am not.
That was part of, it was right before we entered into the standards movement, about dealing with the same type of moving towards the Mendelian, but actually had students both physically doing an experiment because you couldn't have the animals at the time we were doing it, but doing it with a class of about 20 people, and there must have been at least 20 different rebops, creatures created because of what you were given. So it was much more physical than mental.
Okay, so I did something similar to that. I'm sorry, I didn't know it by that name. Yes.
Okay.
Yeah.
Danny?
Well, yes, with marshmallows and toothpicks, right?
Yes. All right. You've been around as long as I have.
Yes. So I think well, I'm going to make a comment, Miray. So one of the, in our group, we did end up with the guided integration, only we went maybe by a process of elimination rather than the way you kind of walked through it. So we didn't really talk about those possibilities of, those initial ideas, like the male, the female, the two, like all of those. But we were saying how it was, let's say it was not scripted, how it was guided. Then we talked about, is there both content and practices, and could we identify those? So that's just what I want.
Yeah, so thanks for making that that explicit, because like one thing that is really sometimes challenging but also have lots of affordances is just like we are really looking at a task without seeing the students interacting with the task and trying to make some anticipation of how students might potentially engage intellectually in this particular task. So that's why, like, generally it's, I think, a good practice to first look at the task and then try to think about like how students may approach this task, of course, in different ways, but like, how will they think about this question? Like, what are these set of questions really helping them to think about? So that is just like one way of approaching it first. And the other thing that I generally suggest, given that this framework is a little bit more complicated than the math framework, is the elimination. So the first elimination I suggest is just like really look carefully to the task and do you see any evidence without making any judgment about its complexity, that whether there is any evidence of potential engagement in science practices. If so, what are they? Like here, for instance, we see, oh, okay, there is data. Students could potentially engage in interpreting data. So that is one way. And then this takes you, okay, there is evidence of scientific practices. Then the next thing to think about is just like, is this task clearly stated within a particular content or not? Here, the task is clearly about genetics. We see that it's about genetics, but no judgment about like at which depth students will engage in that content. So deciding on that, we see that there is evidence of content and also evidence of practices. So this automatically takes us to the integration column. And then in the integration column, so I will just go back to the framework. Oops, sorry, there are only 3 categories now that we need to make a decision about. So if I'm on the integration already, it means that this task is either scripted integration, guided integration, or doing science. Then the next is to really think about the depth in students' thinking that the task is inviting them to potentially engage. Do we see any script? Do we see any guidance? Is it more open-ended? So those are then the next things that we may want to discuss once we just identify which column we are in within the framework. Yeah, so I see some comments in the chat box that yes, it is definitely really important to engage teachers to think about anticipating students' thinking and strategies and possible solutions and different ideas that students could potentially bring up that we can use as a resource as they're engaging in the task. So that initial thinking is sometimes challenging, but really provides lots of affordances that I especially see the benefits when I work with my pre-service teachers. Danny?
One of the things that I heard you say here that I think is important to think through is this potential, right? That the task by itself has potential, because in the end, it's about how the task is operationalized in the classroom that determines what cognitive demand, like where it falls really on the tags. And that's something that's been kind of very rich for conversation for some of us, at Ohio University, thinking through tasks like this.
Yeah.
Right? Because even though this task we may have placed it at the guided integration, a teacher may really make it scripted integration.
Exactly. So
Right.
That's where I will be going next. But I see that there is one question in the group, so I would like to take it before I move on, because it's definitely the direction that I want to take next in the presentation.
My question is, as you talk about anticipating students' results, have you done actually having a classroom where you've presented the task and recorded and knowing what the potential student results, students' questions or confusions might be, which is very similar to the work of Lillian McDermott out of the University of Washington?
Yeah, that's a great question, and thanks for asking that. So not with every task, because I do lots of PD or teacher preparation where we analyze tasks with teachers, and I do not have opportunity to do that with every task. But the one, just to make it concrete, like the one that I shared with you. So the PCR task is the task that was designed by the project team that I was involved with. So I had a chance to see that task being used in various different kinds of classrooms. That really helped me to have a window into students' thinking and what are different ways they're approaching to that task, which also shaped our redesign of this task to really bump it up in terms of its cognitive demand. And we intentionally decided to make it guided integration, right? So there were clear guidance integrated into the task because we wanted students to think about certain things in certain ways. So yes, I did that with some tasks, but not all of them.
Thank you.
Yeah, thanks for asking. Okay, so I will move on because I'm just trying to watch the time as well, so that we can also have some discussion at the end, hopefully. But as Daniel, am I saying your name right? Sorry, I just want to.
Yes, Danielle, that's good.
Perfect. So is kind of is already asking about is just selecting cognitively demanding tasks is definitely important, but that is not sufficient. So tasks like cognitively demanding ones provide rich opportunities for students learning. But from research and also from our experiences in the classrooms, they only set the stage for students' intellectual engagement, but does not guarantee it. We know that especially like cognitively demanding tasks have a history of being transformed once they are placed in real classroom settings. So informed by these kind of transformations that have been happening in math and science classrooms, the task framework that, again, some of you might already be familiar with, was developed. And again, in our recent thinking with Mary Kay and Walter Doyle, we made some slight modifications in the language in the framework. But it consists of these 3 phases that helps us to think about the level and kind of student thinking throughout the full trajectory of a lesson, meaning from its design to how it is introduced in the classroom, to how it is being enacted with the students and the teachers. So this first phase in the framework is related to science tasks that students are assigned to work on. So it's about the level and kind of thinking in which students could potentially engage as they work on the task. So this is what we have been discussing so far. The second phase of the framework focuses on the setup of the task and framing of the intellectual work. The lessons can be framed, for instance, for students as doing school, that is engaging in a set of activities because they are required to do those activities, or they will be graded on these activities, or that their teacher asked them to do those activities. But sometimes the lessons can be framed as doing doing science, that is, we are really trying to make sense of and figure out this phenomena together. So the third phase is about the enactment of the task by the teacher and the students, and really focusing on the level and kind of students that students actually engage as they are working on the task. And prior research has indicated again and again that even when cognitively demanding tasks are selected and set up in the classroom at high level, the level and kind of thinking often declines once students go about working on these tasks. So in recent work with my colleagues, we examined video records of a set of science classrooms in which the same mostly NGSS aligned cognitively demanding tasks are implemented in various different kinds of classrooms. Our close examination of the classroom instruction across these studies helped to begin to gain insight into the instructional factors that played a role in maintaining, sometimes declining, the demand on students' thinking, both in the setup and enactment phases of a lesson. So what you see on the slides are some examples of those instructional factors that play a role for maintaining or declining cognitive demand, such as framing the lesson as figuring out, pressing for evidence-based reasoning. Those are the things that often support maintaining the cognitive demand. Emphasis on correctness or completeness of ideas, sometimes exploring without really an overarching goal in the lesson, are the things that we identified mostly were associated with the low-level student thinking during the enactment. So these analyses really helped us depicting the qualitative portraits of instruction during which students' high-level thinking and sense-making was maintained or not throughout the trajectory of science lesson. While these analyses were helpful to explain what happens during the instruction that shapes students' opportunities to learn, they are difficult to conduct within larger number of classes, especially at scale. So in my current research, I started to grapple with thinking about developing ways to measure when and how rigor in students' thinking is maintained or declined throughout the trajectory of a lesson. So in collaboration with colleagues, we developed the instructional quality assessment in science, informed again by the work in math education led by Melissa Boston. So we refer to this tool as IQA Science. So it helps to assess the degree to which students engage in high-level thinking and sense-making in science classrooms. It consists of 4 rubrics, which are mapped directly into these phases of the task framework that I just recently shared. to understand in depth the rigor in designed, framed, as well as enacted opportunities for students' learning. So there are 4 rubrics. The first rubric focuses on the task as designed and their potential for students' thinking. The second rubric focuses on the level and type of thinking as framed while setting up the task, mostly in the beginning of the lesson. The third rubric helps to make a holistic assessment of the level and kind of thinking in which students engage and the degree to which they engage in sense making. And the last one focuses on the rigor in students' thinking during the concluding whole group discussion. So these are the ones that we call rigor rubrics in IQA science. So we piloted these rubrics within a local context in 9 secondary school science teachers' classrooms. And based on our analysis, chi-square tests of random effects revealed that between teacher variation on IQA science was significant. So this suggests that IQA science is really promising in their ability to capture between class differences in the quality of instruction with respect to rigor. Also recently, we examined using the rigor rubrics, the quality of instruction in group of biology teachers' classrooms during their implementation of cognitively demanding biology tasks and their students' performance on assessment aligned to the science task. And our analysis showed that maintaining cognitive demand, rigor in the whole group discussion, and years of teaching biology are all associated with an increase in student learning gains. So the rigor rubrics seem to predict student learning outcomes. And recently, as part of an ongoing partnership with a large urban school district, we refined IQA science and added talk rubrics. I know talk has been an interest in the group. So we are in the process of seeking ways to use these rubrics to support teachers' learning rather than just using it for assessing instruction. So the task rubrics help, the talk rubrics helps assessing teachers' attention to students' thinking and their lived experiences. And 4 of the rubrics focuses on teachers and the students' contributions to talk to assess the degree to which they are being accountable to the learning community and accountable to the standards of reasoning, knowledge, and the process of sense making. So the rigor rubrics, just to sum up, combined with these talk rubrics, requires primary attention to how students think in science classrooms, the disciplinary activities that students are assigned in the classroom, and the kind of talk in which they engage as they work on these tasks. And also again, the rubrics together focus on assessing instructional quality at the instructional core. So that is the way the teachers and students interact around science. And the language in the rubrics attended to the changing vision for science instruction. So it focuses on the 3-dimensional vision of science learning. And our goal, as we are moving forward, expanding and also using the IQA tool, is that it will be used to enhance teaching and learning. And our emphasis is not on teacher evaluation, but rather understanding and improving teaching and teachers' learning. So I will end it here for us to have some discussion, hopefully with your questions. But thank you so much for listening and opportunity to share my work. I will be happy to answer any questions that might have come up now based on the talk.
Thank you, Miray. That was a wonderful presentation. I know a lot of folks in the group are familiar with the analogous ideas of the task analysis guide and mathematical task framework for mathematics. I find it fascinating to see how this is also being used in science with a good deal of adaptation and enrichment. So thank you for your presentation. I also found it interesting that you're working with Mary Kay Stein. Many folks in this group are familiar with Mary Kay's work, and of course she's been a close collaborator with Peg Smith, our last presenter. And as I understand, Mary Kay was your dissertation advisor. And also you've working with Walter Doyle, who is sort of the granddaddy of all this work.
Exactly.
So that's anyway, but any questions from the group? Is there anything in chat?
Yeah, well, thanks, Greg. So I was super lucky to work with Miray and then think about how those ideas apply in science context. So yes, I think there are some questions. So just feel free to jump in and ask, please.
Yeah, feel free to unmute and ask. Kay, do you have a question?
Oh, yes, sorry about that. Sure.
I noticed that you're unmuted, Kay and Bill, so I thought maybe you had questions, or Jan.
No.
I have a question too.
Okay, Constance. Please.
What I'm getting from this is what I've gained, or what I think I've gained over the course of years of dealing with science instruction, is that the tasks that are developed by people with expertise, and the expectation that teachers should develop their own tasks in the classroom within the stresses under which they are under is not going to lead us to effective science education in the long run in terms of looking at the different dimensions in particular. And I'll go back to, and I don't know, Lydia, if it's still around, the cognitive demand vertical axis that you had was the cognitive demand that was developed around 2010, 2011 in ODE, which went horizontally, where they tried to categorize different tasks, what the cognitive demand required, going from memorization on up. I think the difficulty that departments have, as well as universities, is there's so much, we've learned a lot in terms of how to do, but it comes back to how do you actually implement in a large enough way that you're really having an impact beyond a single school district or a single state. So that's the next key, which also demands not just having a state superintendent say this is what we're going to do. It requires a lot of background preparation. So just a comment, I think you're on the right track, and it's a matter of...
Oh, sorry, you muted yourself. We are missing the last part of what you are saying.
It requires a lot of work. Thank you for what you're doing.
Yeah, exactly. I definitely agree with you. And I see professional learning as being central and really critical when it comes to think about how to really support these opportunities in the classroom. And teachers are, as always, really critical, and they are the change agents. And giving them the agency really requires to support their thinking. So most of my work is actually in that space. So as a teacher, and really co-thinking with the teachers, thinking about how to enrich these opportunities for students. That's hard work, but I think we can do it together. So, but definitely scaling up is challenging. Yes, thanks so much for sharing that.
One of the things that your comment, Constance, reminded me of is how much honestly money is going into the development of instructional materials that are educative for practicing teachers, and so to help them think through. So it's like a prepackaged thing, which was a big no-no. I mean, not so long ago, but now it feels like the field has swung in the other direction, but with providing the tools to be able to use this material in a way to support learning. So that's one comment that made me think of. The other is so one of the things that you said, that maybe we shouldn't expect teachers to come up with their own materials, which is what prompted that thinking about the first comment, is I found it, and I think it's been around for a long time in work with pre-service teachers or with our practicing teachers, is to think about how to change curriculum. So like I find materials, and so now if I evaluate it and I think about where I want it to go, and then the work of the curricular development or preparing for teaching becomes about how to go from point A to this point B. And that's the space that I'm finding very interesting with pre-service teachers right now, is how to help them think through that and how to support them on the job, for example, in their professional internship, those kinds of things.
Exactly. Yeah. And I think like teachers will continue to design their own lessons too. I'm not definitely against that. So, and I think it is just like, it is really critical to give them a lens to think about how to really align the kinds of tasks that they want to create for their students with their goals for their students, because sometimes that misalignment creates tensions. So, and tools like this really help them to think about different components of a lesson and really trying to think about their opportunities and affordances for students thinking. So, even when we create those really well-designed curriculum, they will require some modification because they will need to be adapted to local context, and different contexts will have different needs. So still, I think it's important to give them agency to be able to do those modifications, but do them more informed. So that's again the part that I think some professional learning will be super critical.
And it's
Thank you very much, Miray. This has been a wonderful wrap-up conversation, something that's always important for any lesson in the classroom that teachers often forget, is to have a conversation that pulls us all together. So thank you for the wonderful conversation. In order to complete our agenda, we have to call this to a close, but thank you again for being with us. Thanks everyone for participating so actively in the breakout group and in the wrap-up conversation.
Yeah, thanks so much, and thanks for the opportunity. And I really appreciate all the wonderful questions and comments and co-thinking with me. And I will be leaving, but like if you have any questions, comments, suggestions, please feel free to reach out anytime. And thanks again for the invitation. I really appreciated that.
All right, thank you so much.
Bye.
All right, this was a nice wrap up to our year-long theme on cognitive engagement in mathematics and science. We've been blessed with 3 wonderful keynote presentations.